let's talk about the stellar halo of the galaxy. As we all probably know, or think we know, galaxies like the Milky Way assembled through this hierarchical formation process predicted by cold dark matter. What you're looking at here is an animation from Mina Helmy, where you see different satellites coming in, and they're all color-coded uniquely, so you can see how they go over time. And what you see is there's this great variety of behavior that happens over cosmic time. At early times, the timescales are short, things happen fairly quickly, and things remain sort of in the central regions of the galaxy. As time goes on and the virial radius of the halo grows, the apicenters go to larger radii. You see a lot of radial orbits, things plunging through the center and splashing back on the other side. You see this nice plume here. So there's this great variety of structure that we think is happened in our galaxy and in all other galaxies to different degrees. Of course, the challenge is that we actually live down in here, and so observing the structure is quite challenging, but that's what we want to talk about today. But this basic process is a fundamental prediction of cold dark matter theory, and so we'd like to understand to what extent we can dissect this picture in our galaxy as a starting point. Catherine already showed this picture. This is a view of this sort of process just from the photometry of stars in the northern and southern skies from the Sloan Digital Sky Survey. Points are color-coded by distance, and you see some of the more dramatic events that has shaped the stellar halo, including the Sagittarius stream here and down here, these thin cold streams, GD1 and Palomar 5, which are disrupting globular clusters, and then a variety of other sort of interesting and for a long time somewhat confusing clouds and plumes of material, including the so-called Monoceros ring, the Hercules Aquila cloud. There's a whole bunch of other clouds and fluff around here that until recently were sort of difficult to understand. So looking just in configuration space or just in sky coordinates is challenging because stars can get mixed around over time, and they become hard to sort of identify as discrete objects. And so that's motivation for going to some kind of phase space-like quantity. So I want to motivate why we might want to try to measure phase space properties of stars. And by phase space, I just mean some combination of x, y, z, vx, vy, vz, such as, for example, the energy and the angular momentum, which is a common way of thinking about stars in the halo. So what you're going to see here is an animation. This is made by Anna Bonazza of several disrupting galaxies in a fixed potential. And what you see is that they evolve around over time. They develop leading and trailing arms, multiple wraps to get quite complicated, but they stay fairly confined in energy angular momentum space. And then at one point, a new satellite was introduced. It's now going around. Now a third one's introduced. And the basic point you're supposed to take away from this diagram is that things are fairly messy on the left, right, in just configuration space, but they're rather more concentrated in energy and angular momentum space. This is a very simplified picture. Reality is much more complicated. When you actually have a live halo, you can have energy exchange between the halo and the disrupting objects. But this is just meant to motivate why you might want to try to spend a lot of energy to measure this type of information for lots of stars. So that's what we're trying to do. There's many groups trying to do this now. But the basic idea is to identify accreted systems in the stellar halo of our galaxy. What you're looking at here is, again, the same diagram for a simulated stellar halo from the Aquarius group, where they do particle tagging. And you see all these different lumps, which are due to the accretion history of the, which is due to the assembly history of the simulated halo. So phase space has a longer memory than configuration space. These quantities are at least approximately conserved, but that's a big approximate, and we can talk about that later if you're interested in. The problem, though, is that this information is very expensive to obtain. You have to measure 3 positions and 3 velocities for stars, and that's a very challenging thing, as we'll see in a moment. But you can learn a lot. So here's an example. This is 3 different simulations from the Aquarius group. And on the top panel is the assembly history of these Milky Way-like galaxies. So this is an early former. Most of the mass was formed early. This is a late former over here. And just by eye, you can visually see there's a very different overall morphology of stars in these diagrams. All right, so you can kind of see that just by eye. You can look also, you can see this in many different simulations. This is the fire simulations of Milky Way-like galaxies, where now the color coding is by metallicity. 3 different simulations again. So one thing to take away is these are already quite different from the Aquarius simulations, which we can talk about that more later if you're interested. Also, these simulations have a disk, and that's what you're seeing here. So disk stars lie in this part of the diagram, and they're red, they're fairly metal rich. And then the different types of galaxies have somewhat different histories, and so again, there's different distribution of stars in these diagrams. So there's a few challenges to measuring these kinds of things. I just want to point out one here. So this is that same halo I showed before. The red now are all the stars from a single progenitor. So one thing you learn already is that, in fact, while the main sort of body of the system is over here, there's a spray of material elsewhere. So it is actually fairly complicated to interpret these diagrams. But these red points, this is from a single progenitor, are scattered across the entire sky. So this object would never be seen in that Sloan field of stream because it'd be everywhere, and yet it's one of the most massive accretion events in this simulated halo. So the halo of our galaxy is probably, perhaps, teeming with additional accreted systems that you're not going to see just in an RA deck projection map. So as you probably are aware, there's been a revolution within the galaxy over the past several years, being driven by the Gaia satellite, which was launched in 2013. It is mapping the entire sky and delivering proper motions and parallax constraints for over 1.5 billion stars down to a magnitude limit of 21. That's really amazing. It will eventually produce colors and grism spectra for a subset of those stars. And then it's delivering radio velocities, precision radio velocities from the calcium triplet down to a brightness of about 14th magnitude. So that's great. There's been a huge amount of studies published over the past year focusing on this bright subset in the very local halo within a kiloparsec, where there's been a lot of this measurements of phase-based properties of stars in the Milky Way. However, there's a problem when there's this big gap between the radial velocity limit and the limit from parallaxes and proper motions. So the lack of radial velocities for fainter targets is a big limitation of Gaia. And furthermore, the parallaxes are actually fairly poor distance indicators for stars beyond about 10 kiloparsecs. The parallaxes are too noisy to be good distance indicators. So those two facts combine to really motivate ground-based follow-up spectroscopic surveys to fill in this gap between the radial velocity limit and the proper motion limit. And so that leads me to tell you about the survey that we're running. It's called the H3 survey. It's for hectoshell in the halo at high resolution. Hectoshell is a high-resolution fiber-fed spectrograph on the MMT telescope, which is a 6.5-meter telescope at Arizona. Hectoshell is fairly unique for having a large field of view. It has a 1-degree diameter field of view and can attain spectra of 200 objects at a time. Resolution and wavelength range is here. The strategy is to target a large area of the sky for the reasons I motivated a few slides ago. So we're going to cover 15,000 square degrees with 1,000 fields, so a sparse tiling strategy, totaling 200,000 stars. The selection of targets is extremely simple. It's stars that have parallaxes that are greater than 2 kiloparsecs away from us, and a magnitude that's brighter than 18th magnitude. Observations began about 2 years ago, and we've collected about 90,000 spectra to date. The team is mostly focused at CFA and also University of Arizona. It's a small team, which is a lot of fun for a survey. I want to come back to this point because it's really, really important. It's sort of technical. But all previous surveys of halo stars prior to Gaia had to make a more complicated set of selections to identify these fairly rare, distant, low metallicity stars. By using Gaia to do a parallax selection, we are unbiased with respect to any other type of population in the halo. So it gives a really clean, unbiased view of the halo for the first time. So that's one of the niches of this project. This is the footprint of the survey in galactic coordinates. So gray is the overall targeting regions, and blue are the fields observed to date. So we're focusing on high latitude fields. As I said, for a lot of these stars, the parallaxes are too noisy to be really useful for distance indicators. So we developed an elaborate pipeline program to estimate distances along with metallicities and radial velocities and so on. The program's called Minesweeper. It's written by postdoc Phil Cargile. These are just some simulated mock observations. I want to focus on this, not the whole thing. This is actual results for one star, and I want to focus on these 2 points here. So the Gaia parallax for the star is consistent with 0, but it's very noisy, so not useful. But the spectrophotometric distance puts it at about 95 kiloparsecs. So the basic idea here is if you can measure a surface gravity and a temperature and place the star on an isochrone, then you can read off the luminosity, and the difference between the flux and luminosity gives you the distance. So that's how this is done for stars with noisy parallaxes. This is a rogues gallery of some interesting objects in the survey. These spectra are unfortunately not typical. These are signal to noise of about 20, whereas the typical of the survey is about 6. But you see here a metal poor star at 25 kiloparsecs, a K-giant at about 50 kiloparsecs. There's a molecular carbon feature going back to Raj's talk. C2 is right here, so this is a strongly carbon-enhanced metal poor star. And we see a weird selection of stars, which from my trained eye looking at galaxies, I originally thought they were somehow redshift 0.0 galaxies, but no, they're just cool stars with very high rotational broadening, about 50 to 100 kilometers per second. So these are stars, this cumulative histogram of the distances just for stars which are either selected to be giants or in the kinematic halo or low metallicity. And you see we have 100 stars out beyond 50 kiloparsecs. And that'll at least double when the sample is done. Okay, so I want to come back to this diagram that I was motivating earlier, energy, angular momentum. This is what you would expect to observe if the galaxy was completely smooth. So this is a smooth Mach catalog. So what you're looking at is halos. So the catalog has a halo component and a thin and a thick disk. So this is the halo component here, and this is the thick disk here. All right. So if the galaxy was smooth and boring, that's what we would see. In fact, this is what we observe. This is only focusing on the giants. So you don't look at all the sort of nearby stars. It gives you a pretty good view of the entire halo. So you go back and forth. You see a lot of structure. And if you're not used to looking at these kind of plots, I'll help guide your eye. So this is 0, and again, over here is prograde stars, so stars orbiting with the same direction as the disk, and the other side is the retrograde. Okay, so let me introduce you to a couple of these clumps we see. So this is Sagittarius, this big mass of material up here, the Sagittarius stream. This structure here is much narrower, you might have noticed, than the smooth catalog. This is the structure that there's a great debate raging in the community as to whether to call it the Gaia sausage or Gaia Enceladus, but they're basically more or less the same thing. But this component is a fairly massive component to the halo and was discovered with Gaia, hence the name. And it has very radial orbits. That's why the distribution of angular momenta is very narrow, and it's also narrow in other projections of the angular momentum as well. So it's very radial orbits, and it peters out right about up here, which corresponds to apocentric distances of about 30 kiloparsecs. And that in turn corresponds to a break radius in the density profile of the halo. So you see these things kind of are coming together. This is a combination of the thick disk down here, and then way up here, these are stars that are 10, 15 kiloparsecs above the plane and 20 kiloparsecs from us. And they're associated with this monoceros ring, which we think, from work from Shervin Lepore and Catherine and others, that these stars were kicked up from interaction with Sagittarius. There's a structure over here, which you'll see more clearly in a later diagram, which is being referred to as the Sequoia event for reasons I cannot explain. But there's not a lot that's been discussed about this event yet to date. But one thing we know is that from previous work and also from these data, it's a little more metal poor than this object. And because it extends to less bound energies, and we see it directly in the actual data, it extends to larger radial distances as well. In addition, there's a little feature here, this bridge region, which corresponds to a stream that Amina Helmy identified in the late 90s. And finally, up at the top here is a population of fairly metal poor and on average retrograde stars. So they span a wide range, but on average they're shifted over to the right, which is the retrograde component. So there's this sort of diffuse, low binding energy retrograde component, which has a very broad distribution in radii. So that's the overall view. One thing to take away from this is that, and this is work that's ongoing, but from these data, we've resolved most of the structure in the stellar halo. We're going to do a detailed quantitative analysis of this, but just by eye, you can kind of pick out and identify that most of the major components of the halo have been resolved out. If you just slice this now in metallicity, again, you see mostly the thick disk stars and a little bit of Sagittarius. As you go to sort of moderate metallicities, now you really clearly see all the components at once. This one, this one, this one, this fan up here, and Sagittarius. As you go more metal poor, and then more metal poor, and draw a line, you can see that, again, this metal poor component has this, on average, very retrograde component to it. We can look at the metallicity properties or distribution as a function of radius in the halo. And there's a couple interesting things to see here. First, again, you can see discrete features. This is Sagittarius, which is fairly metal rich. This, we think, is the in situ stellar halo, which I'll mention again in a moment. But what's kind of remarkable is actually that the metallicity gradient is really quite flat over the entire halo. And if I just take averages and show the lines, it's really flat. And it's really quite metal rich. Rather more metal rich than what people used to think of the stellar halo. And part of that, again, goes back to the selection function. In a lot of previous work, they were cutting out these metal rich stars, sometimes by definition, because you didn't have the Gaia information to give you the full view of what was going on. So the halo is actually quite metal rich. You can then make that same diagram now, again, separated by orbits that are prograde, retrograde, or radial. And again, you see here is the dominance of Sagittarius. Here is this Gaia Enceladus structure, mostly. And then here is this, on average, quite metal poor component, which, compared to the other populations, again, has a pretty flat radial profile. And if you look carefully, I plotted in gray up here stars which are above this line here. So what's shown in these bottom panels is a distribution of metallicity versus alpha to iron. And there's a clear sort of second population up here. And this is what we think of as these stars have thick disk-like chemistry. And so we associate that with what's known as the in situ halo. So the idea is that these stars were born in the galaxy and kinematically heated to halo-like orbits. And those stars are really confined to within about 10 kiloparsecs from the center of the galaxy. For the accreted component down here, you see that Sagittarius is fairly alpha poor. As you go to this structure here, it's somewhat more alpha rich, and then here is a little more alpha rich. So see different chemical properties as a function of the orbits of the system. You can then just bin up and plot histograms, again, in 3 radial bins, just to give you a sense of things. In sort of the intermediate radial range, the population is consistent with being dominated by a single progenitor. I say that because this dotted line is a simple chemical evolution model, and it fits the data quite nicely. Whereas in the left and right panels, you see clear evidence for multi-components. So again, within the inner part of the galaxy, this is clearly the in situ component, the metal-rich component. Over here, this is mostly Sagittarius, but again, there's this very distinct metal-poor component at larger radii. And we're just beginning to kind of try to understand the origin of what that means for the origin of the halo. I want to very briefly mention, so I talked about LZ, but in the halo shouldn't necessarily care about Z as opposed to any other direction. This is LY, and in fact, you see much more contrast in this direction, and that's because Sagittarius happens to lie almost exactly in the Y direction of the galactic coordinates. So this is Sagittarius. If we select stars this way and just plot their vectors, I don't know how it's going to come out, but you can clearly see, hopefully, these arrows. You're seeing the stream motion of Sagittarius in the sky. So we have this beautiful sort of 6-dimensional oh, geez, how did that happen? Okay, yeah, I'm done. Yeah, so we're trying to actually map out Sagittarius in this way as well. Okay, so the stellar halo, a couple quick highlights. Beyond about 10 kiloparsecs, we think the halo is comprised entirely of accreted stars. At shorter, closer distances, it's a combination of this in situ component and an accreted component. The metallicity gradient of the halo is remarkably flat. And the stellar halo is rather more metal rich than a lot of previous work, due in part to the selection functions of previous surveys. The majority of the halo seems to be resolved into discrete chemical orbital structures. All these things were known before. What this survey allows us to do is give us a complete view of the whole halo and get a complete accounting of the distribution of these objects with radii and what is their relative mass fraction contributions to the halo, et cetera. So that's all work that's ongoing. But it's late, and so I really just want you to remember one thing, which is that the survey H3 is a new unbiased survey of the halo aimed at resolving the accretion history of the galaxy. That's it.
Okay, let's take some questions. Next.
I learned a long time ago that it was plausible to think that at least part of the halo stars came from disrupted globular clusters. You say that beyond 10 kpc, it's all accreted. Presumably the globular clusters are mostly not accreted. What fraction came from globular clusters, if any?
That's a good question. And it's hard to know, I think. I mean, I think, honestly, from some of these, well, I'm not going to go back, but given that we've resolved a lot of the halo into these larger structures, I think kind of by inference, you can rule out there being a dominant contribution from globular clusters. That's maybe one way to look at it. Another way to look at it is that we know that globular clusters have this really unusual chemistry in their stars. And so by doing detailed chemical analysis of stars, which we can't do for these spectra, but from other work, there's been accountings that it's a small fraction of the stellar halo. But we could look at it this way as well.
Does this change our view as to the amount of disruption that globular clusters have suffered?
Well, there's a lot of debate on the globular cluster front because it depends a lot on how big you think they were initially. And so if they really were like 100 times more massive, then it would cause, I think, a huge problem. In the sort of more conventional view, I think it fits in just fine.
So you mentioned rhinoceros looking up there. Can you see other structures as well? Because we were interested in some structures beyond rhinoceros.
But in the rhinoceros region, are you asking?
In other regions of the sky, actually, but also a large latitude, but parallel to the disk. And maybe you just don't have enough stars.
Well, so, I mean,
Try and reach
it's worth keeping in mind that, if I can zoom back, forgive me, the footprint is such that we really, so we're planning to go down to B of 30, but right now we actually are only going down to B of 40.
Yep.
And so anything
Yep.
that's closer to the plane, we're never going to see. So I was surprised even to see monoceros stars up this high.
Yeah, that's exciting. So, okay, I'd like to teach.
Yeah, and they're on very circular orbits, those stars. So they're in this weird configuration where somehow they got kicked up by Sagittarius but still maintain their circularity. So it's interesting to ask what that means.
Just before you go, come on in and we'll unplug you and transfer.
Do you have any favorite other elements of stars?
So for most of the spectra, where signal to noise is like 6, we're really happy with iron and alpha. For a subset, we do actually expect to be able to measure, so in that spectral window, there's a wide variety of other elements. Most of them are a little garden variety, other iron peak elements or other alpha elements. With 1 or 2 S process elements, in fact, for that one carbon star, you see a very strong impeded also an S process element, which is what you expect for carbon stars. So we probably can get an S process element, but we can't get, for example, like an R process element. So that's kind of
All right, well, David, sorry, we kind of need to wrap up. Thank you very much, Charlie, for the presentation. Last but not least, Santi, you just had it.
Yep. Okay,
Beautiful.
perfect.
Take it away.
Okay, perfect.